Hello and welcome back to another thermal expansion video. And in this video we're going to take a step away from the theoretical and general, and we're going to look at some real-world materials and how the instantaneous thermal expansion compares to the average thermal expansion using real data. So if we take a look and we plot the instantaneous thermal expansion versus temperature for different materials, and this will be in degrees Celsius. Look at 0, -50, 50, and 100. This will be in units of times 10 to the -6, 1 over degrees Celsius or degrees Kelvin. So this is 100 times 10 to the -6 per degree C. And for temperature, this will be 100. This will be 50, 0, and -50 degrees Celsius. So if we look at a quote-unquote normal material where the average CTE is a really good measure for the way it behaves in a normal temperature range, room temperature being about 20-25 degrees C, we can look at aluminum 6061, and this is T6, and you can see that there's some curvature there, but it's not that great. So the average CTE, which would be a constant on this plot, or a straight line horizontal, the average CTE is a really good measure. And so for most metals, that is the case, especially around room temperature. But when we start to look at different materials, for example, nylon, the story is a bit different. And Delrin, the story is different. Nylon and Delrin are both polymers. So this is Delrin 100, and this is nylon 6. And you can see that the CTE changes, the instantaneous CTE changes quite drastically in this temperature range, between -50 and about +40 degrees or +80 degrees Celsius. And so the average CTE will not accurately predict the displacement of a Delrin or nylon material in this temperature range. And if we look at the material that we manufacture at ALLVAR, ALLVAR Alloy 30 responds like this. This is ALLVAR Alloy 30. So its CTE will change with temperature as well, and it won't be as steady as aluminum, but it will be more constant than a Delrin or a nylon. So if you can design and manufacture components and systems with Delrin or nylon and the CTE isn't a big problem, then ALLVAR will definitely suit your needs. And you can look at other videos that we have that discuss how ALLVAR can be used. So if we take this instantaneous CTE and we start to look at how it influences the strain we would calculate, we'll start to see the difference between the average and instantaneous CTE's result on our calculations. So this is strain in percent, and we'll have 1% up here, 0.5, 0, -0.5, and -1% strain. And this is temperature, again in degrees Celsius. And this is -40, this is +80, and this is 20 degrees Celsius. So we're looking at room temperature approximately plus or minus 60 degrees C. And if we take a look at the nylon's strain versus temperature, if we use the instantaneous CTE, which is a function of temperature, the strain we would see would look something like this, where that curvature that you see gives us this change across temperature in nylon. So this is nylon 6. And so if we look back at the average CTE and we look at the equation for that, it's strain 2 minus strain 1 divided by T2 minus T1. So if we look at the extreme temperatures, plus 80 degrees C and negative 40 degrees C, that tangent line gives us this average CTE for nylon. But that's not what we actually see or use if we're using it to calculate. So what we actually do is room temperature is where we have zero strain, not this negative temperature over here or this lower temperature. So we start from here and we extrapolate that straight line up and down. So this is the same alpha average. And you'll notice that at room temperature it's exactly the same as the instantaneous CTE. But at these extremes, there's a discrepancy between our average CTE and the instantaneous CTE, or the strain calculated using the average CTE and the instantaneous CTE. And that difference is 0.08%, both at the top and bottom. So that's a 0.08% strain difference between what you see in the real world and what you calculate using an average CTE value. If we take a look at Delrin, we see something very, very similar. And we're going to use kind of the same scale. This is 1.0, 0.5, 0, negative 0.5, and negative 1. This is strain in percent, and this is temperature in degrees Celsius. 20, 80, negative 40. So Delrin, although it has a slightly different curvature in the alpha instantaneous versus T curve, it shows somewhat of a similar response as the nylon 6. So this is Delrin 100, and that's what you would actually see in the real world. And if you take the average CTE from room temperature and extrapolate it up and extrapolate it down, you'll see a similar discrepancy. And this is 0.09%, so it's close to what you would see in the nylon, maybe a little bit worse. Something interesting is that it has a tail down here, but it doesn't have one up here. So you have a very good correlation between the average and instantaneous CTE down to about negative 10 degrees Celsius, and then it starts to diverge very quickly. So this difference between what happens in the real world and what we calculated using the average CTE, we can look at from kind of an error perspective. And so what's the error associated with assuming the average CTE and not using instantaneous CTE? So the strain calculated using alpha average minus the strain calculated using alpha instantaneous is what I'm terming the difference in strain, or the error associated with that difference between those two. And if you want to understand how this will impact a component, you can take your difference in strain due to this error and multiply it times L1 being the original length, or the length at room temperature of your component. And that would be the difference in length, or the error associated with a real-world component compared to the calculation. This will actually be negative. So that's your error right there at the extreme temperatures. And you want that error to be less than the tolerance of your component, or the tolerance in your error budget for these extreme temperatures. And you can see that it scales linearly with the length of a component. So for example, if you have 0.09% error times a 2-inch part, that would be the length, or the original length of that part, your delta L error will equal 0.0018 inches. So that's almost 2/1000ths. So your part that's in spec at room temperature, even if you calculate it to still be in spec using the linear coefficient of thermal expansion, at the temperature extremes you're going to see a positive 2/1000ths and a negative 2/1000ths offset compared to what you calculated using average CTE. So it really just depends on the tolerance of your system, on the length. If this is a 4-inch part, then you're looking at about 4/1000ths. If it's a 1-inch part, then you're looking at 0.9/1000ths, 1/1000. So it just really depends on the size of the component, on the tolerance that you have to hold, as well as the temperature range. If you're in a tighter temperature range, -40 to +80 doesn't really matter, then you have a very good correlation in that small temperature range.